Hello everyone, I'm Paul and today we're solving problem 1039, minimum score triangulation of polygon. This is a medium one and here we are dealing with shapes. So first we will solve this visually and then we will go with the code. We are given an integer array values representing the vertices for some polygon and these are sorted in clockwise order. In case you know what a polygon is, it's a shape with at least 3 sides. So for example, a triangle is a polygon. A square is also a polygon. This is also a polygon, okay? So we are given some array. Let's say we are given this 1, 2, 3. And here we have 3 values, so we have 3 vertices and we need to order this in clockwise order. So let's say we have this triangle. This is 1, this is 2, and this is 3. And now we need to do something called polygon triangulation, which is we need to take our polygon and split this into triangles. Here we only have one triangle. And we need to sum the score for each triangle. The score is the product for the values in the vertices for each triangle. In this case, it's 1 times 3 times 2. The result for this is 6. And we need to return the minimum possible score that we can achieve with some triangulation. In this case, we only have one triangle, so we just return 6. Now, what happens if we get this array? Here we have 4 vertices, meaning we have a square. And this is 3. Remember, this is sorted in clockwise order. So 3, 7, 4, 5. And we have 2 possible triangulations here. One is we can take this triangle with a score of 3 times 4 times 5, and we take this triangle with a score of 3 times 4 times 7. The result for this is 60. The result for this is 84, and the sum for these values is 144. So this is one possible triangulation. The other possible triangulation in this case is we can take this triangle, which has a score of 5 times 7 times 4, and this triangle, which has a score of 5 times 7 times 3. This is 140, and this is 105. The sum for these values is 245, and 245 is greater than 144, so in this case we return 144. Now let's say we have 8 edges, and this is a lot. We can have multiple triangulations here. For example, this is one possible triangulation. This is another possible triangulation, and so on. We can have multiple triangulations here. So we need some sort of standard process to solve this. And we know that we can only use triangles, and triangles have 3 vertices. So we can have 3 pointers, I, j, and k. So let's say this is index 0 and I is initially here. And let's say that j is here in the last index. How many triangles can we build with these 2 pointers? Well, we can put k here, for example. And if we do this, we can build this triangle. If we have k here, we can build this triangle. With k here, we can build this triangle. With k here, we can build this triangle. We can also build this. Or if k is here, we can build this. So let's say that k is here, and now we can build this triangle, and this has a score. And the main observation right now is that here and here we have 2 subproblems. We are splitting this entire thing in 2 parts. So now we can solve each of these subproblems with dynamic programming. We are storing the score for this triangle and we are adding the score for each of these subproblems, and we are repeating the same for every possible triangle, for every possible combination of I, j, and k, and this is how we can get the minimum possible score with some triangulation. We are trying every possible triangulation, and we can do this because of the constraints. We know that n is smaller or equal to 50. This means that we can think in terms of n cubed. So let's say we are in this subproblem. Here we will have again the I pointer, let's say it's here, the j pointer, let's say it's here, and we are doing the same. Let's say the new k pointer is here, and we can take this triangle, we add the score for this triangle, and now this is a new subproblem. So here you can see how we have different branches. From one possible triangulation, we have two different subproblems. And from this, we can have two more subproblems. From these, two more subproblems, and so on. And this is only if we start with this triangle, meaning if we start with this triangle. But we could start with some other triangle. For example, if k is here and we start with this triangle, now we have this subproblem and this subproblem. So we always have two new subproblems until we have no more vertices left. And remember that values is sorted in clockwise order, and this is very helpful because let's say we're trying to get these the elements for this subproblem. Well, we can take a subarray for values which goes from I to k. Okay, so this represents this entire chunk of vertices, this, and these vertices. Similarly, for this subproblem, we can take values from k to j. And this represents this, and these vertices. And now we can run a new DP here and a new DP here, and we add the scores with this score, and we keep the minimum possible score among every possible triangulation. So this is basically the entire approach. Now with this in mind, let's go with the code. Here I'm building a top-down recursive dynamic programming because I think this is more intuitive. So we are calling this function dp. This takes I and j pointers. And first we have the base case, which is if we have no triangle, we return 0. So if j minus I smaller than 2, we return 0. And why are we using 2 and not 3? This is because we need to fit k in between I and j. So if we have less than 3 vertices, we can't form a triangle, so we return 0. Just to be clear, this is we have no triangle. Else the result is infinity, and we need to return this result. Why are we using infinity here? Because we need to return the minimum score for any possible triangulation. So we start with infinity and we will return a lower number. Here in between, for k in range from I plus 1 to j, the current score is values I times values j times values k. And the result is the minimum among the result and the current score plus our two subproblems. Remember our drawing. First we call dp from I to k and dp from k to j. And just to be clear, here we try the current triangle or the current score, and split remaining vertices in 2. Okay, so finally we can just return dp from 0 to the length of values -1, and something very important, we need to cache this entire thing, which is we are storing the result for every possible combination of I and j. So this is it for the code. I think this is right. Now let's submit this and see if it works. As you can see, this works and it's very efficient. Here, time complexity will be big O of n cube, and space complexity will be big O of n square, because we need to cache this. So this is it for the problem. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.